Welcome to our first lesson on the energy unit. We're starting off with a lesson on work. Specifically, we're looking at mechanical work, which is represented by the capital letter W. And work is energy used by applying a force to displace or move an object. And the equation for work is force times the displacement. Now notice that force and displacement are both vectors, and work is a scalar. And that is true all the time. So we're looking at when force and displacement are in the same direction, that is when the force is doing work. Let's just take a look at the units for a second. So the units for force, we know, are newtons. And for displacement are meters. So this Newton meter is equivalent to what we call joules. And we use the symbol capital J to represent joules. And just to kind of take a look at it spelt out, remember that newtons are kilogram meters per second squared. So a joule is a kilogram meter squared per second squared. Excuse me. So we'll take a look at a couple of brief examples just to get the basics down. So if we're lifting a textbook upwards, 0.5 meters with 20 newtons of force. And I mislabeled a diagram. I should say 20 newtons. So we've got this book and we're using our hand and we're pushing it upwards with 20 newtons and we lift it up 0.5 meters. So work is the force, which is 20 newtons, in the same direction as the displacement, which is 0.5 meters. So we get 10 joules. And then here in example 2, we are walking across a 3-meter room while holding a textbook. So if I'm holding this textbook, it means I'm holding it upwards. So the force that I'm applying here is that direction, but I'm walking in a perpendicular direction. So these things are not in the same direction. They're completely perpendicular, which means that in this case, work is going to be 0. We're not doing any work because we're moving across the room, not going up or down. But you say, I may not be putting a force perfectly perpendicular or in the same direction. So yes, we do have to be able to consider situations with an angle. So here I've got a person pushing a box and their shoulders are above the box, so they're really pushing down and forward on the box. So you can see the applied force here is drawn at an angle, and we're using it at the angle theta. So which part of the force is actually causing it to move forward? Well, if you draw out this applied force here, there's going to be a component forward and a component into the ground. And that component into the ground is going to be counteracted by the normal force, by the floor, right? So we're not actually contributing all of our applied force to work. It's only going to be the horizontal force. So the only part that actually matters is the part that's in the direction of the displacement. So it's the part going forward here. So if I'm looking for this x component and I'm using the angle theta, then I'm going to have to use cosine. Right, because cosine of theta is the adjacent, so that is my x component there over the hypotenuse, which is the force that we start with. So the component that I'm actually going to use is FA times cos theta. So that means that instead of writing my equation like this, I can change F to f cos theta, and then we're just going to write them as scalars. So f d cos theta. Okay, the equations mean the same thing, and you will eventually learn as you get a little higher into mathematics and physics that I actually use this dot for a particular reason here. It's a type of multiplication with vectors called the dot product, and it results in a scalar when we use it. But for now, all you have to know is that it means to multiply. So we'll do one example here that involves the direction of the force and the displacement not being in the exact same direction. So we'll use the same diagram above. So we're pushing a box across a room, and this time there's friction acting on the box. It moves 1 meter, and we want to know how much work friction does. Okay, so not how much work the person does, but how much work friction does. So we have to keep in mind here that the direction of the displacement is this way, and the frictional force we see is the opposite direction. So we're looking for the angle theta, which is going to be all of this. So since they're perfectly opposite directions, theta is 180 degrees. So when I solve for work equals the force we're looking for work for times the distance travels times cosine theta. So it's 10 newtons. Sorry guys, it's kind of terribly messy. I'll try that again. So we get 10 newtons times 1 meter times the cosine of 180 degrees, and 10 newtons times 1 meter, that gives us 10 joules. And the cosine of 180 degrees, if you plug that into your calculator, or if you've done math with this already and you know what the value is, you'll know that the cosine of 180 degrees is -1. So our answer is -10 joules. So therefore, friction does -10 joules of work. So when the direction of the displacement and the force are in opposite directions, we end up with negative work. And that will happen every time that they're in opposite directions. So now you know we can end up with negative work, and that's a perfectly good answer. We can use an angle, and we're going to use this equation. Or if they're in the same direction, you can still consider this equation here, because the cosine of 0 degrees is just 1. So you end up back with work equals F times D. So remembering that equation will work every time.